Welcome to the 7th Neuro-Inspired Computational Elements Workshop. We are very happy to have the event held here this year. We'd like to thank our sponsors and also our host with all the arrangements they've put together here for us. My name is Murad Okandan. I'm one of the organizing committee members. And our organizing committee and our local organizing committee are really the key people behind the workshop coming together. I'd like to acknowledge both Hemant and Caitlin Stuckey and the local organizing committee here. They've done a great job getting a lot of logistics and local arrangements in place. It's been very wonderful. To give a very high-level view in this introduction, I'm going to reuse some of the slides that we've used in previous workshops also, but what's really driving this workshop and kind of the events that are going around is a very long burn. This isn't something new. People have been thinking about this for a very, very long time. There's neuroscience, Kahali Ramon, and other people that have looked at neural systems saying, there are things here, how is this working? Going back even further. On the computation side, the difference engines, an example, the difference engine here by Babbage and Ada Lovelace and others, Leibniz, incredible work around, incredible thoughts around how do we actually compute? What is computation about? How can we make it more efficient? And then coming closer, looking at the early origins of the electronic computing machines, there have been some incredible devices, systems that have been built, and getting closer, the transistor, the semiconductor industry, and our current state, just in general, being able to create these very intricate, very powerful digital systems that are doing great things with software and different ways of using them, but in essence, they're still back to the difference engine. These are mathematical tools. These are things that have a program or a certain set way of working. I think a lot of the people in the audience and maybe the community in general has realized and is working harder on this paradigm shift in computing, which is going beyond that stored program or kind of conventional computing approaches, exact mathematical approaches. Not to say neural computing doesn't have a mathematical description to it, but there are, I think, things that are potentially more involved and maybe beyond what we've explored so far. So again, there are lots of different ways of making these systems and using them, but what are potentially the two key things we're going to use these systems for? The first one is neuroscience and medicine, actually building these systems as an example of how neural systems might work, and then trying to understand the neural system's biology better. That's going to have incredible outcomes, we believe. The second way, or kind of the second application area, is actually taking those systems and then applying them to new ways of controlling things or new ways of predicting physical system behavior, which again, we're not able to do right now because maybe efficiency or time limits with the current systems that are out there. So maybe a quick look at how the systems are being used right now. How are we making these next generation AI systems work? There are really three broad categories you can imagine. One is software. Basically just running on conventional digital systems, just getting them to run faster and faster. Another way is software and accelerators using GPUs, TPUs, other AI hardware that are, again, making things better, but it's still a conventional computing system at the base level. And what we're really excited about is this new platform direction, which is potentially non-von Neumann, non-Turing machines, where, again, you're representing, processing, storing, and recalling information in different ways that really hasn't been done before. So where are we going? What is really going to come out of all this work? If you think about what we use all these systems for, again, from very early stages, starting with H.G. Wells, the suggestion he had was catalog all the information in the world, turn it into the World Encyclopedia, and use that information to make better decisions. He wasn't thinking about an electronic system. He was actually thinking about a physical print library of all the knowledge that's available to humankind, and then here we can make better decisions using that information that's available to us. Arthur C. Clarke in the 60s imagined, again, a very similar concept, but slightly different now, actually using electronic systems, saying, well, there will be a world library, everything will be gathered, and he estimated that will be done about 2000. So, well, not too far off. He was actually fairly close. And then the next stage is the world brain, where all that information that's available to you, now we can run AI systems on top of that to generate new knowledge. More recently, again, another potential direction in terms of how do we use information, all the information that's available to us. Well, not just electronic systems or not just knowledge, but look at humans as individual nodes in that knowledge network. And we are essentially doing these functions. We are gathering information, we're making predictions, and then that sampling process that we do, we then throw another layer on top of us through our networks. We pass information to other people, then they make decisions based on all the information they're gathering. So you can sort of layer this in multiple levels and think about where we might go. Again, not only in human interactions, but now put an electronic layer of all these new AI systems in between that's maybe filtering information, maybe modifying the information. What is really going to happen in that kind of an environment? We need to be very careful and cautious about how this technology gets evolved and deployed in those kinds of scenarios. There are potentially great advantages and potentially some great risks as well. So thinking about the neuro-inspired, neuromorphic next-generation computing systems, we're really aiming to converge leverage the convergence that's in place right now, looking at neuroscience, theory and algorithms, computational devices, microelectronics. There's a very large application area, and some of the machine learning sort of software-based systems are having great success. But there are a larger set of problems that are not really being addressed, potentially with, which we would potentially address those with the systems that we're discussing here and potentially developing in the near future.